Hi, my name is Asher Kahn-Krell. I am a graduate student in Dr. Jay Zhang's lab at UAB. Today I'll be sharing some of the work we've been doing on biomanufacturing of micromyocardial or organoids through suspension differentiation and looking at the sort of improved yield, purity, and quality of these biomanufactured tissues. So to give a little background, as many of us in this consortium know, that we can take adult cells, differentiate them, or sorry, reprogram them into iPS or induced pluripotent stem cells, and then use those cells for differentiation into multiple different cell types, and then have them applicable for downstream applications. In our field that we're working in of cardiac tissue engineering, our interest is in taking those iPS cells, typically differentiating them into cardiomyocytes, then producing some sort of tissue structure, whether that's spheroids or cell sheets or direct myocardial injections, and then using them for the primary purpose of repairing the heart following an infarction. You can also then use these tools that are developed in the process for studying developmental processes or for studying drug treatment and other such tools. The specific goal that I have, though, with my project is to work on these two sort of steps right here. So taking this process we typically do in 2D of iPSC differentiation into cardiomyocytes and then cardiomyocyte manufacture into tissue structures, and doing that all in sort of a new, more biomanufacturing type of system. And so I'll talk through sort of the two steps, the differentiation process and then the organoid or microtissue production process. So to start off, the generation of spheroids or the differentiation process is something we recently published on, and you can find our publication online in Frontiers. And here's sort of the basic steps of that, which mimics the traditional method we use in 2D of a 12-day small molecule treatment method followed by a metabolic purification. You can see that down here in the timeline. And here's what this sort of spheroids look like over time during that process. And then beginning on day 9, we see beating. And then on day 12, we see a pure beating population of cardiomyocyte spheroids. And you can see that beating down here in the bottom right. We then took these spheroids that we produced over this 12-day process and assessed them for homogeneity, for just basic characterization, including diameter, looking for necrosis. And what we found is that overall, the spheroids we produced in this process are consistently homogeneous with sort of similar expression of cardiac structural proteins, including troponin and alpha-actinin throughout, as well as having minimal and diffuse necrosis or apoptosis, as you can see from the tunnel staining in the top right. So although there was some apoptosis that we found in these spheroids, we were excited to see that it was not localized to any sort of core region, which would be the main concern for these sort of several hundred micron diameter tissues with nutrient transport and diffusion to the center. Additionally, one thing we found is that the spheroid diameter from iPSC to cardiomyocyte does not change significantly. We did find there was some increase in diameter when we cultured these out to 30 days. However, we're typically seeing that mostly from aggregation, not from additional cell division. And the tunnel positive nuclei, although it is in the sort of 5 to 10% range, we find that that is mostly due to the differentiation process, not to some sort of lack of nutrient supply in the core of these spheroids. Then further, after characterizing the structural nature, we wanted to look sort of more at some of the gene expressions and some of the functional status of these suspension differentiated spheroids. And when we looked at the yields compared to the monolayer process, we found that there was a trend of improved yields. However, it wasn't statistically significant. Additionally, when we looked at some of the gene expression, we didn't see major increases in some of these traditional isoform switching markers of maturity after just the initial 12 days of suspension culture. But when we did culture these out further to 30 days, we actually saw some pretty significant increases, both in the ventricular isoform switching of the myosin light chain, as well as the troponin I switching from the 1 to 3 isoforms. And so this was exciting, sort of what we would expect from doing 3D culture of cardiomyocytes. And previous studies have shown that when you culture cardiomyocytes in this 3D type systems, you do see this improved maturity. But it was exciting to also see that when we did the entire differentiation process in 3D. Along with that sort of gene expression levels, we did look at electron microscopy images of spheroid of cardiomyocytes produced either in suspension or monolayer. And one of the major markers of functional maturity, the sarcomere length, we did see significantly improved in the suspension cultured cells. So that's sort of that first step of now being able to do these processes that are typically significant amounts of work in monolayer and scaling that to a 3D scalable system. So we then wanted to say, okay, well, now we have these 3D spheroids without having to dissociate them or turn them back into sort of this traditional monolayer method. Can we then take those and form sort of larger, more organotypic type structures? And we did this through the addition of other cell types. And these organoids, as many of you know in the fields of lung organoids, or as liver organoids is another sort of field where this is being used. These organoids have a more mature structures, which can allow for the use for all kinds of different applications, including implantation, toxicity screens, disease modeling. And several people have developed sort of tissue-like organoids for cardiomyocytes, but typically they use those monolayer differentiated cardiomyocytes and then form them into these organoids. But we felt that by taking our 3D structures that we've already created and just sort of adding in these other cell types, we can more rapidly reach this mature organotypic structure that we're looking for. So we're going to talk through some of the preliminary work that we've done in this field. So our overall objective for this specific project was not as much to go and do all those downstream works, but really to create this tool, this initial application of these organoids. And so our goal really was to get to the size, moving from that 200 to 300 micron spheroid to combining them for to produce a larger diameter organoid. Show this continuous beating to maintain that survival over sort of longer periods of time, making sure that as we grow and make these things larger, that we're not getting sort of a region of necrosis in the center. And then finally, look at all that maturity and the functional status of these organoids. So the process that we are taking to produce these organoids is, so we've scaled that 3D differentiation process, which is sort of the most complicated cell type culturing process that's necessary for these organoids. And additionally, we use iPSC-derived endothelial cells, smooth muscle cells, and cardiac fibroblasts. Because those have the ability to expand, we are culturing those as a monolayer and adding those into these structures as single cells. So the cardiomyocyte spheroids as spherical structures are either combined without the other cell types with endothelial and smooth muscle, or with endothelial, smooth muscle, and cardiac fibroblasts in low attachment U96 well plates. And in those 96 well plates, over 1 week, they fuse into these organoids, which we then continue culturing after that 1 week in low attachment 6 well plates, or with larger numbers of these in flasks. And the studies that I'm going to show you going forward are sort of our first round of studies, and these actually do not use the smooth muscle cells, and the endothelial cells that we used in these initial studies were HUVECs, not iPSC derived. But this is sort of the overall goal of where this is going to go moving forward. So this is the initial work that I was talking about. We looked at multiple numbers of cardiomyocytes per organoid. And I will say that the standardization between the different conditions is actually the cardiomyocyte number. So the ratio of endothelial and fibroblasts stays the same, but we use the same number of cardiomyocytes, whether there's cardiomyocytes only or cardiomyocytes plus the other cell types. So as you can see, we add together the spheroids, the cardiomyocyte spheroids, and in the top, it also has the additional cell types. And actually, after 4 days, we already see sort of a spherical structure forming. The cardiomyocyte only appear to take longer to sort of tighten up and form that nice structure. But we did see fairly consistent diameters when we used similar cell numbers. Then we cultured these out to 3 months. I do have additional data at the 3-week, 1-week, and month time points, but we don't have time here to go through that. So I'm going to focus on what was the most interesting finding we had, which is that we were able to culture and keep these spheroids viable up to 3 months. And as you can see in the video here on the left, they do continue beating and fairly vigorous, strong beating at that 3-month time. These are about 600 to 700 microns at this time point. You can also see from the trichrome stained sections at the top that the organoids still have a pretty solid uniform structure. And then we did staining down at the bottom for multiple markers you would expect to see with the different cell types in these organoids. And I'll go through those in a little more detail real quickly. So the first thing we wanted to look at was the tunnel staining to see if we have any sort of necrosis in the core of these organoids. And as you can see on the left, the organoid that has the multiple cell types versus just the fused cardiomyocytes actually has significantly less apoptosis as demarcated by fewer tunnel positive nuclei. Additionally, that the tunnel positive nuclei are diffusely spread throughout and not localized, as you see on the right, in the core of the spheroid. So this is sort of what you would expect as you get to these larger diameters, this lack of nutrient transport to the core and necrosis. But what's amazing is that even at 3 months, we don't see that in the multiple cell type organoids. And so this is something really exciting going forward as we talk about trying to produce these thicker tissues with maintaining viability. Additionally, and some of that viability may be explained by the rapid and diffuse spread of the other 2 cell types that were added to these specific organoids, including the CD31 positive endothelial cells. As you can see, they are even beginning to form sort of vessel-like structures here with lumens, and that's something we're continuing to explore further. And they're elongating and stretching throughout, as well as the fibroblasts, which you can see are sort of stitching the cells in the different tissues together and integrating, as other groups have shown, fairly closely with the cardiomyocytes themselves. So this is all very exciting and something we're continuing to explore further. So what comes next? In our work, we're continuing to do more quantitative examination of these organoids and doing this in a more standardized way. As I said, those are only with the initial group of cells, but we're continuing to repeat these studies with these 3 different groups and looking at sort of all of those different time points. So we're hopefully going to have a lot more data to show you in the next few months going forward with these organoids. Thank you to everyone in my lab for all the different funding agencies that provided support to be able to do this work, and to all the UAB core facilities that we rely on to collect all that data.